All right, guys. So we just finished looking at the examples of writing electron configurations. I want to show you kind of how this actually looks in terms of an atom. So here we have a sample of scandium, which is number 21 on the periodic table. And you're going to see how these orbitals kind of build up around the nucleus. So like we said, we fill that 1s orbital first. When that one is full, we then get a 2s orbital. Notice that this one's larger as we move away. Then it goes into 2p. So 2p we said has 3 different orbitals that are that dumbbell shape that go in the different directions or orientations. And after 2p, we have to fill 3s. And then we'll fill 3p, which has those 3 orbitals in the different orientations, the different locations where electrons are likely to be. And then once 3p is full, then we fill 4s. And then after 4s comes 3d. That was that weird hybrid one. But remember, these are going to be those clover leaves that yet again have the different orientations. So this is a 3-dimensional structure, and each of those lobes are areas that you're likely to find electrons around the nucleus of an atom. So I just wanted to show you what that looks like in terms of an atom itself. We did some examples of writing electron configurations. For honors, there are some exceptions to the rules, some that you have to rearrange the electrons slightly. And this has to do with stability. So atoms are going to be most stable when they have full or half full orbitals. So each of those orbitals where we said S has 1 orbital, P has 3, D has 5, F has 7. If each one of those orbitals has an electron, so say we're going to do this with the D sublevel. So D, we said, could hold 10 electrons total. That is the most stable with it being full. But the next most stable arrangement would be if that D sublevel can have 5 electrons. So half the number of electrons in that orbital. So like if we can have an element that has an arrangement ending in 3d5 instead of 3d4, that is going to be the most stable. So for our transition metals that are in that D block, or we haven't talked about the D block yet, but for the transition metals, those group B elements that are in the drop down bridge, the energies of the S and the D sublevel are so close together that elements a lot of times will not completely fill the S block or that S orbital, and some of those electrons will transfer into the D orbitals to make them full or half full. So I want to show you what this looks like. So we're going to use chromium as an example to start. Chromium is number 24 on the periodic table. So filling this in with an electron configuration just like we did. We fill in 1s, which can hold 2 electrons. Now we're down to 22. Then 2s, which can hold 2. So we have 20 left. After 2s comes 2p, which can hold 6 electrons. So we have 14 left. Then comes 3s, which can hold 2. So we have 12 left. After 3s is 3p, which we said can hold 6 electrons. So we have 6 left. After 3p comes 4s, which can hold 2. And then we have 4 left. So after 4s is 3d, which we would put 4 in. So we said this is not very stable, having that 3d4. So what we'll do to make it more stable is we will borrow one of these from the 4s and change this into 3d5. So we simply move one of those electrons over because they're so close together in energy. So looking at the picture over on the right, you'll notice like here is 4s, here's 3d. So one of these electrons just hops over into the other sublevel because they are very close together in energy. So the correct way to write out chromium would be the 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Showing 4s is half full and 3d is half full as well. Let's look at silver. Silver is another one that does this. Silver is number 47 on our periodic table. I'm going to write out the normal configuration so you can see it. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. So yet again, remember D is going to be most stable if it has 5 electrons or 10. Whenever it has 9, it's not very stable. It would be more stable if it had 10. So it will steal one from that S block and make this 10. And this only happens in the 4th and 9th column of the D block. So you're going to see this with where chromium is, that column going down. So chromium, molybdenum, tungsten, seaborgium. And then where silver is that 9th column in the transition metals. It starts with copper and then silver and then gold and then rhodium. So you do not have to do this for every element. You're only doing it for that 4th and 9th column of the transition metals. All right, so let's look at how we write electron configurations using the periodic table. So the periodic table, the way that it's arranged is separated into blocks, and the different blocks are associated with the different sublevels. So there's an S block, a P block, a D block, and an F block. And this is going to match up with the location of the outermost electrons in that atom. So for example, the first 2 columns on our periodic table, so the alkali metals and alkaline earth metals, their outermost electrons are going to be in an S sublevel. So those 2 columns we refer to our S block. And here's how the periodic table is going to be split up. So those first 2 columns are S block. We move helium over to be included in the S block of that first row. The P block are our other representative elements, the last 6 columns of those group A elements. The transition metals, that bridge in the middle, we refer to as our D block. And then the inner transition metals, we refer to as our F block. So we don't deal with these very often. But with the periodic table way, you're essentially going to read the periodic table like a book. So these match up with your rows on the periodic table. So we have row 1, 2, 3, 4, 5, 6, 7. So as we're going through, we have to go through each row of the periodic table. It's like we're going to go through 1s first because we're on the first row going through the S block. That's that whole row. So then we have to go through the second row, which has an S block. So that's the 2s. Keep going straight across and then that goes to the second row P block. This does take a little bit more getting used to. If you are not feeling comfortable with electron configurations, I would recommend sticking to the diagonal way. But I do want to kind of show you a couple of things regarding using the periodic table way in case you would like to do it this way. So that principal energy level, that number that's associated with our electron configurations, is based on our row number. So for the S and P blocks, the principal energy level is equal to the row number. So like I said a moment ago, we're in the first row S block, so that was 1S. The second row S block was 2S. Second row P block was 2P. If we are in a D block, because the S and D blocks tend to go out of order based off of energy, for the D block, our principal energy level is going to be the row number -1. So if you look at chromium, which we did a moment ago, that is a transition metal in the D block. It is on the third row of the periodic table. So, or excuse me, the fourth row of the periodic table. But the D block, we do the row number -1. So 4 minus 1, that would be in the sublevel of 3D. And for the F block, it's going to be the row number -2. But we do not use these very often. So just to show you an example, if we look at, sorry, my computer went crazy. If we look at titanium, titanium is number 22 on the periodic table. And I'm going to kind of sketch a periodic table so you can see how this looks. Okay. So kind of filling in for titanium, which would be here in the D block, essentially. We're going to have to first go through the first row S block, which includes helium. So remember, helium is over here. So that would go through 1S, which is 2 elements wide, which is why it holds 2 electrons. That's the entire first row. So then we would have to go to the second row, which has an S block. So 2S, which is 2 elements wide. So that's 2S2. Going straight across on the second row, there is a P block as well. So we would have to go all the way through there. That's 2P, and the P block is 6 elements wide, which is why it can hold 6 electrons. That would be the entire second row. So then we would have to go to the third row, which still does not hit the transition metals. So we would go to the third row that has an S block, and it is 2 elements wide. Keep going across. That also has a P block. So 3P, which is 6 elements wide. So we've used up 18 of our electrons so far. Then we get to the fourth row, which is the row that titanium is actually on. We have to go through the S block, which is 2 elements wide. Then we are into the D block. But remember, the D block, we said the number, it's the row number -1. So the fourth row -1 is going to be 3D. And titanium is the second element in the D block, so it's 3D2. I will see if I can find an additional video for anyone that wants to try using the periodic table way. But like I said, the diagonal way is easier to use, but you have to practice drawing that diagonal. All right, so I do want to show you that there are some configurations that whenever we get to some of those larger elements, the configurations would be a whole line on a page. So there is a shortcut that you can do. These are going to be referred to as abbreviated or noble gas configurations. With these, the shortcut is you can use the symbol for the noble gas before the element that we're writing the electron configuration for. And that symbol is going to take the place of all of that beginning stuff that is repetitive. And that would leave us only the row that the element is on to write our electron configuration. So to show you how this works, let's look at cobalt. And cobalt is number 27 on the periodic table if you need to find it. Now this one's, you know, not at the bottom of the periodic table, but you still have to list out the locations of 27 electrons. So what we can do, and I'll draw a little periodic table up in the corner so you can see. That is not to scale, but cobalt would be here roughly. We want the noble gas before cobalt. So you want to go up one row and all the way over to the noble gases, all the way to the right. So go up to the cobalt is on the 4th row. So go up to the 3rd row and all the way to the right. That is the noble gas of argon, which is number 18. So what we can do is we can write the symbol for argon in brackets, and that accounts for 18 of our 27 electrons. So then we only have 9 left that need to be placed. The hardest part comes next of figuring out how do you start the rest of your configuration, because that argon takes the place of all the beginning stuff of the 1s2, 2s2, 2p6. So you want to figure out what row of the periodic table cobalt is on. So this is on the 4th row of the periodic table. So we are going to start with 4s. Whether you use the periodic table way or the diagonal way, we're going to start with 4s. That can hold 2 electrons. So we have 7 left. After 4s, we're in the D block. So that's our 3d, 7. And that is the abbreviated configuration for cobalt. I'm not going to do uranium because we typically don't do the F block elements. Those are kind of weird ones. I'm going to change this to, let's do lead. That's another large one. It's something that we use pretty commonly. So lead on the periodic table is number 82. So lead, if you put your finger on it, go up one row and all the way to the right. The noble gas before lead is xenon, which is Xe. That takes the place of 54 of our 82 electrons. So that takes a lot out of the beginning stuff. So then we only have 28 electrons that need a place to go. So if you look, lead is on the 6th row of the periodic table. So we're going to start with 6s. So we said S can hold 2 electrons. We're down to 26. After 6s is where it gets tricky, because those inner transition metals are actually part of the 6th and 7th row on the periodic table. So if you're following your diagonal way, it jumps from 6s to 4f. And F, we said, can hold 14 electrons. So then we're going to have 12 left that need a place to go. Well, after 4f, it comes back up to the D block. So you end up, let me change colors real fast. You end up doing the S elements, then going down and doing the F block elements, and then coming back up to do the D block elements. So you're kind of moving back and forth a little bit, and it's simply because of they arranged the periodic table so it will all fit on one page. So after 4F14, we have 12 electrons left. So we come back up to the D block. So that was 5D, which can hold 10, and then we have 2 left. So then we get to the 6P, which will hold those 2. For noble gases, I'm going to switch radium to radon so you can see this. Radon is a noble gas. You cannot simply write the symbol for radon in brackets. That doesn't count. You still have to use the noble gas before radon. So if you're at radon, go 1 row up, and you would have to start with xenon and then write out the configuration for that row. So always make sure that you're using the noble gas before the element we are writing an electron configuration for, even if it itself is a noble gas. All right, and that's where we are going to stop today. Tomorrow, you're doing the flame lab. Make sure that you wear closed-toed shoes and have something to pull long hair back. Tomorrow, we will pick up and do the electron configurations of ions because you will have to write those as part of your flame lab. And we're also going to look at orbital diagrams.